Pre-biased transistors are useful for your digital circuits. They can be used for level shifting, inverters, and driving loads. They promise to reduce the parts count on your printed circuit board. The printed circuit board itself can be smaller, and there's a potential for cost reduction. In this short video, we're going to explore the differences between the conventional and the pre-biased transistor circuit. Then, for the die-hard engineers, we're going to perform some circuit calculations so that you have a better idea of how these circuits operate. Starting with the conventional circuit, we have R1, which serves as a current limiting resistor, connecting the microcontroller to the transistor base. We have an R2, which operates as a shutdown resistor, so that if for some reason the microcontroller is in a high impedance output, the transistor will be sure to turn off. And some typical values are 1K and maybe 10K for R2. The pre-biased transistor is almost identical. We still have an R1, we still have an R2, we can have values such as 1K and 10K. The difference is in the circle. For the conventional circuit, we see that the circle encompasses only the transistor, while for the pre-biased transistor, the circle encompasses both resistors and the transistor. We could define the pre-biased transistor as having three elements inside a single case. That would include the series R1 current limiting resistor, the shunt R2 turn-off resistor, and the transistor element itself. This could be an advantage for your circuit, such as when a small SOT23 pre-biased transistor is selected. You do not need to install this R1 or this R2. So your parts count goes down and you have the potential to make your board smaller. As promised, here are those circuit calculations. We begin with a microcontroller with a 3.3 volt source, a pre-biased transistor with R1 set to 4.7K and an R2 set to 47K. Finally, we add the transistor with some resistive load. Our known voltages are 3.3 volts DC and 0.6 volts DC. The current flowing into that 4.7 k ohm resistor is calculated as 3.3 minus 0.6, all divided by 4700, which is approximately 574 microamps. There is a current flowing in this resistor, calculated as 0.6 divided by 47,000, which is approximately 13 microamps. That leaves a current here of approximately 560 microamps. If we assumed a forced beta with a ratio of collector current to base current is equal to 10, we conclude that the maximum current for this particular setup is this base current times 10, which is about 5.6 milliamps.